Hello, welcome back to Organic Chemistry. We're going to be talking about E1 and E2 elimination reactions now, which are the side reactions of substitution reactions, but we might want to do them deliberately. So here we are with with E2, our nucleophile, which can also be a base. So this is a base. The nucleophile is behaving as a base. It's taking away a hydrogen from the neighboring carbon, and I've drawn it carefully so that the hydrogen is opposite the chlorine. They're in plane, called anti. So these two are in the same plane. Hang on, my board's not quite focused. So as we can see, the hydrogen is on the neighboring carbon, and this nucleophile, or base, better described, will take the hydrogen away, and the electrons from the bond then go and attack into the antibonding orbital of our halogen, in this case of our leaving group. So this would be the normal leaving group if it was an SN1 reaction, but an SN2 reaction, but this is an E2 reaction. So the same thing is happening. We've got a second order reaction, remember? 2 stands for second order reaction, which means that both the base, this nucleophile, and the main compound are in the rate determining step. So this is dependent on the concentration of the nucleophile and the concentration of our substrate, unlike a first order reaction. And we can see a similar attack, that electrons are going into the antibonding orbital of the chlorine in this case, and we have a concerted single transition state. Resolving that, we can see we get a double bond, and we also see an interesting thing, that we only get one product. We cannot turn this round or this one round so that our X, Y, and W, X, Y, and Z groups are differently organized. The X must be on the same side as Z, and Y must be on the same side as W, whatever they are. So this gives us only one product, which is unlike other reactions, which we will come to. The E1 mechanism, on the other hand, goes via a carbocation, just like SN1, and so the slowest reaction step is loss of our leaving group, giving a positive charge on this atom here. And just like in SN1, if we get to here, this is free to rotate, and so there are 2 products for this reaction, which we can draw depending on whether this rotates here or in the other plane. So it's got to rotate to interact with this hydrogen so that the electrons from the hydrogen can go in. Let's draw that. So here we have our carbocation, and our electrons from the hydrogen, which I haven't drawn on, can go directly into this positively charged orbital because it has no electrons in it. And then that means this bond should be aligned with it, but it can either be aligned with this side or it can be aligned with the top side, because this is symmetrical. It's flat, planar, with this electron orbital with nothing in it sticking out in the other plane. That gives us 2 possible products, either the E or Z enantiomer, depending on what these side groups are. So either with X and W on one side or with X and Z on one side. So now I want to draw your attention to the similarity between both of these reaction mechanisms and the stabilization mechanism of our carbocation, that if we have a methyl group, for example, over here, and one of the hydrogens is aligned so that the electrons in its orbital are in the same plane as the orbital that has no electrons in it, then we can have a transfer of electron density, sort of lending electron density from the bond to the empty orbital, which spreads the charge around, which means that if we have a tertiary butyl group, for example, with the tertiary carbon in the center, these are much more stable than a secondary or a primary carbon, because the positive charge is delocalized, is spread around more of the molecule. It's spread around this hydrogen, and the one at the back. And these groups, because if they're methyl groups, they can rotate, but we have 3 different hydrogens which at different times are pointing towards one or other of the 2 lobes of this orbital. That is the same or similar to these 2 mechanisms, because in the actual step where the proton transfers, where the double bond is made, this becomes an actual bond. We're actually donating electrons from this orbital directly into the empty orbital or the antibonding orbital in the E2 mechanism. So let's draw those next to each other. So this is our deprotonation step for both of them. A base comes along, it removes the proton, and the electron density goes into the antibonding orbital of the leaving group of the E2, and in this case the base comes along, removes the proton, and the electron density goes into the positive charge in the E1 mechanism. Remember E2 because it's second order, because both the base and this compound are in the rate determining step. E1 because it's first order, the base doesn't matter. Oops. So now we have 4 things that could be happening at the same time when we have a nucleophile and our substrate that can be attacked by a nucleophile. That obviously sucks, because then we would get an awful lot of different products depending on what happens, but we can choose to a certain extent. So we could choose SN2 against SN1 by choosing the nucleophile. Good nucleophiles make SN2 more likely. Bad nucleophiles make SN1 more likely. We can choose it by the substrate. So a substrate that stabilizes the carbocation will tend to be more likely to go via an SN1 mechanism. And a substrate that stabilizes or that doesn't stabilize the carbocation is more likely to be forced to go via SN2. That's why I've put these like this, because then obviously if our substrate is a tertiary carbon, it is more likely to do an E1 than an E2 as well, because we're more likely to get to the carbocation. But there are other factors in play. So most likely it is E1 versus SN1 and E2 versus SN2, but there are other possibilities. So if we imagine an E2 process, it is important in that case that we get this geometry with our hydrogen down here, so opposite and flat in plane to the leaving group, and that will be predetermined by the shape of our molecule, which we may or may not be able to change. But if our molecule is fixed, so it's a ring, and it's fixed so that the hydrogen and the chlorine are on the same side of the molecule, then we cannot do E2. An example of that would be a ring molecule, which is in the Masters Chemistry website, which you have a link to. So if we take this molecule and we have the 2 groups on the same side, so we have something stopping this, and our hydrogen is on the same side, H, so we have whatever methyl group, so let's just put a bond, and then we have 2 on there to stop it from doing anything else. So we reduce the possibilities. If we take this molecule, it cannot do E2 because the hydrogen is on the wrong side. It would have to be down here, and there's a methyl group there. So in that case, it must do SN2. It might do E1, but it cannot do E2. With that aside over, normally what we can control is what is the nucleophile and what is the solvent. So how can we do that here? Well, our solvent isn't particularly important. But what we can do, as it is actually, our solvent is quite important, and the nucleophile is important, because if the nucleophile is a better base than a nucleophile, it is more likely to take this hydrogen away. An example of that would be pyridine. So if we take a pyridine, the nitrogen on the ring, 1, 2, 3, NH, the nitrogen on the ring is quite a good base, but it's not a very good nucleophile. Then it will tend to do an elimination reaction, because it's a good base but a not very good nucleophile. If we have a good nucleophile, OH- for example, then we are going to have less chances of having an elimination reaction, although it won't be zero. If we have conditions where our solvent can take the hydrogen away, so a protic solvent, for example, that will also push us towards the elimination reactions. If it is an aprotic solvent and we don't have a very good base as our nucleophile, then we're more likely to go for a substitution reaction. We're more likely to get a substitution reaction, than we get an elimination reaction. In the first order case, we've got conditions where we're likely to get a carbocation. So we have some kind of stabilization of our carbocation, maybe by methyl groups, and then our solvent is probably helping. And then we want to know, will it do an elimination or a nucleophilic substitution? And that is also determined by how good our attacking group is at causing deprotonation. It is also dependent on how long this sits in solution, because if our carbocation hangs around in solution for a long time, it is more likely to do something else. The faster, the higher concentration of nucleophile we have, even though it doesn't affect the rate of the reaction, it will push it towards doing a substitution. The problem obviously being with a deprotonation that if the solvent is protic, there are a lot of molecules that can take that hydrogen away. The example given in master's chemistry is this, that if we take a cyclohexane with a bromine on one side and two methyl groups on the other side, if we try to do an E2, so if we set up the conditions so that forming a carbocation is unlikely, so we have a non-polar solvent, then we always get this product, because the hydrogen is on the wrong side to be able to be removed at the same time as this bromine. It is not opposite. If we do an E1 reaction, so we set up with a polar solvent, we can take off this bromine and generate a carbocation. But our evidence for that is that if we get this product. This product is more stable, because for the same reason that the carbocation is more stable, a more conjugated, a more substituted double bond is the lower energy product. This more substituted double bond is lower energy than this, but it cannot form via the E2 reaction with this molecule, because there isn't a hydrogen on the correct side for it to happen, so it forms the other product. This one can also form the other product, but it is comparatively rare, because this one is more stable. You might be wondering why this is important. Elimination reactions are important because if we have a double bond in our molecule, we now have a second carbon center that is the functional group. So we could add something across this double bond and have two new functional groups. And what I'm hoping that you're gradually understanding is that organic chemistry is all about taking a functional group and converting it into another one. And in this case, we've taken a functional group and converted it into one that we can now make two. Or if we look here, we can move this functional group. So it was on this atom here, we can move it around depending on what we do. So we've now made this one active, and in this reaction scheme we've made this one active, so we can, to a certain extent, move our functional group around the molecule. It takes a lot of steps, obviously, if our molecule is big, but we have another tool in the toolbox for making the thing that we might want to make. That's the normal way. That is the final goal of organic chemistry, is to make something that we decide beforehand from simple materials.